So we're going to take a little bit of time and learn how to draw Lewis dot structures or electron dot structures. So what they are is a two-dimensional representation of where the electrons are in a molecule. So as we saw before, bonding electrons are indicated by a pair of dots, although usually we use a dash instead, which represents the same thing as two dots because dots tend to be a little bit more messy, but either way is either a pair of dots or a dash. And then the Lewis dot structure also needs to have the lone pairs indicated. So let me go through the rules of how to write an electron dot formula or structure, and then I'm going to go through in this PowerPoint a number of examples. So if you're not exactly sure what the rules are at first, just bear with me and see if you can do it. And I highly recommend following these steps. People like to forget and put electrons in different places, but if you follow these steps, you really will end up doing a lot better, especially finding out if you need a double bond or putting lone pairs, things like that. Okay, so let's see the rules. Okay. So I'm gonna illustrate it by showing the structure of PCl3, and then I'll show you some other examples. Okay, so the first step, the first thing you need to do is figure out how many valence electrons the molecule has, how many the valence electrons, the outer shell electrons. So in order to put them together, you have to know how many they have to work with. So the easiest way to do this is to look at the A group numbers. So the valence electrons are the same as the A column numbers. So for example, phosphorus is in column 5A, so it has 5 valence electrons. And then each chlorine, because chlorine's in group 7A, each chlorine has 7. And so 3 times 7 plus 5 gives me 26 electrons. Now that's really important because those 26 electrons are the ones, they have to be used, and we can't exceed 26. And so to put this molecule together, we have our 26 electrons in order to bond, to give each element 8 electrons. That's kind of our goal. Keep in mind that to find the valence electrons, if you have a polyatomic anion, so if it's a negative polyatomic ion, don't forget that the fact that it's negative means that it has a few extra electrons added as a group. So you want to add whatever the charge is, you want to add that number of electrons. And if it's a polyatomic cation, you need to subtract the number of electrons for the positive charge. So if it's a positive 1, subtract 1 electron, because a positive means that group of electrons or that group of atoms has lost an electron. Okay, so PCl3 has 26 electrons. So step 2, arrange the atoms around the center atom. Generally, we put the least electronegative atom in the center. Usually, we're going to be doing pretty simple ones, so it's usually the multiples that are around the outside. But also keep in mind what I said earlier earlier in the slideshow is that, for example, chlorine only wants 1 more electron, so it's only going to make 1 bond in general. There are exceptions to the rule, but and phosphorus, being in the 5th column, tends to want to make 3 bonds, so it's really good for it to be in the center. But if you find the least electronegative atom in the center, that's also very helpful. Okay, so step 2 means rearrange the electrons. And then you want to put a pair of electrons between the central atom and each of the atoms surrounding it. So what's happened here? I've used up some electrons to make a bond. I've used 2 electrons. So far I've used 6 electrons out of my 26. So I still have, if I had 26 to start with and I've used up 6, I still have 20 electrons. So step 3 is to distribute the remaining electrons to the peripheral atoms to satisfy the octet rule. Don't forget that hydrogen only needs that 1 bond and it's satisfied. So again, follow these rules. Don't worry about the center atom till the end. So if I have 20 electrons left and each chlorine needs 6 more, so I put them on there. So now I've used up 24 out of my 26 electrons. So my final step is to distribute any remaining electrons to the central atom. If there aren't enough electrons on the central atom, even after you do that, you may have to have a multiple bond. So in this case, because I have 2 electrons left, I can put them on the phosphorus. And so now phosphorus has 8, and each of the chlorines has 8, and so everybody's satisfied. So again, first distribute the electrons to the peripheral atoms. Then, if there are still more electrons, you always put them on the central atom. And then you want to double check, and even after you've distributed all the electrons, if the central atom still doesn't have 8, then you will have to make a double bond or a multiple bond. We'll see some examples of that in a minute. Okay, so let's try drawing the Lewis dot structure for SCl2. So first of all, we want to find out how many electrons it has. So sulfur has 6, and each chlorine has 7, so that's 20 electrons total. And so if we take the S in the center and attach it to each chlorine and put a bond between them, we've used up 4 out of the 20 electrons. Now if we distribute next, we're going to distribute the electrons to the outer peripheral atoms first. And so if we do that, we've used up 12 more electrons, so we have 4 left. Since we have 4 left, we place them on the center atom. And we've used up all of our electrons. And then just to do a double check, make sure each chlorine has 8, the sulfur in the middle has 8, and so this atom this molecule is good. All right, let's do another example, COCl2. This time, still, C is the least electronegative element, so I'm going to put the C in the middle, and I'm going to put the other peripheral atoms around it. Let's see, the carbon has 4 electrons, valence electrons, oxygen has 6, and each of the chlorines have 7, so that's 14 plus 6 is 20, plus another 4 is 24, so that's where the 24 came from. If I put the C in the center and I put the other peripherally around them, and then if I make a bond to each of those elements, I've used up 6 electrons, so I still have 18 left. So the next thing would be to, again, give enough electrons to the peripheral atoms so that they all have 8. So if I give chlorine 6 more, the other chlorine 6 more, and the oxygen 6 more, I've used up all my electrons. But you're not done here. You always want to double check that everybody, especially the center, has its 8 electrons. And in this case, you can see carbon only has 6. Now, I can't come and stick 2 more on carbon because I don't have any more left to put on to give. I started with 24 and I've distributed 24, so I don't have any more to give. So this is a case where if you don't have enough electrons, and this is a really, really common mistake, students will put double bonds willy-nilly, but the only time you ever need a double bond is if you don't have enough electrons. If you run out of electrons and somebody still needs 8. So in this case, I'm going to take 2 of those electrons from oxygen and share them with the carbon. Okay, so there you see the oxygen now is sharing 4 electrons and has to itself 4 electrons. So the oxygen still has 8, and the carbon now has 8. Now, why did I pick the oxygen and not the chlorine? Well, that kind of goes back to that earlier slide. Oxygen likes to make 2 bonds. It needs 6 electrons, so it likes to make 2 bonds, whereas chlorine only likes to make 1 bond in general. So that's why I picked it. If they all happen to be the same, there's a situation that will come up that I'll tell you about in a little bit. Okay, so the octet rule is now obeyed. All right, let's look at another example, Cn negative. So first of all, we need to find the valence electrons. Carbon has 4, nitrogen has 5, so that would be 9. But because there's a negative charge, there we add one more electron. So there's 10 total. So we have 10 electrons total to distribute between the C and the N. So the first thing I'm going to do is make the bond between the C and N, which uses up 2. So I have 8 more. And then what did I do? In this case, I gave 2 more, I gave 4 more to carbon and 4 more to nitrogen, and that uses up all my 10 electrons. Well, as you can see, neither of them are happy because they only have 6 electrons. So I'm going to take 2 from carbon and share them with nitrogen. So there's a double bond. Carbon, unfortunately though, carbon still has 6. Nitrogen now has 8, but carbon still has 6. So now I'm going to take 2 away from nitrogen and make a triple bond. And so this is the result, is that carbon and nitrogen will share 6 electrons and then each have 2 electrons for themselves. And it just it's good to, when you draw the Lewis structure, to put the charge of the ion as well. Sometimes you can put brackets around it and put the charge, or just make sure that you write the charge. So let's look at ozone. Ozone, if you draw, you might want to take a minute and stop this and try drawing the Lewis structure for ozone. If you do, you know that ozone has 18 valence electrons. So if you make the 2 bonds to the outer O's and then give each of the outer oxygens 12, you'll have 2 electrons left over that you can give to the center. Then you realize that the center oxygen only has 6 electrons, so you need to make a double bond. But in this case, you're not sure, should I make the double bond from the left-hand O or the right-hand O? So the best answer is that you need to make the double bond to both of them. If you were if your experiments show that both of these bonds are identical to each other, so the way I have it drawn here, it looks like there's one double bond and one single bond, but if you were to measure them, they're actually each the same kind of bond. So this is actually a better picture of what we're trying to see. The one bonding pair is actually spread over 3 atoms. And so it's called a delocalized bond because the bonding pair is spread over more than 2 atoms. So it's actually like each OO bond is 1.5 bonds. The easiest way for us to represent that is shown on the next slide. So if you get a situation like this where you're going to need to make a double bond to the center and the options around from the peripheral atoms are all the same, what you're going to have to do is draw each possibility. So in this case, draw the double bond going to the left-hand oxygen and then redraw it with the double bond going to the right-hand oxygen. And then we show an arrow in between, meaning that actually it's a mixture of these 2 structures. So this is called a resonance structure. And you do have to write both of them. And if there happened to be a 3rd oxygen attached to the center, you would draw a 3rd structure with the double bond going to that oxygen. So again, just keep in mind, as if the peripherals are all the same and you need to draw a double bond to the center, this is the way to do it. Okay, so many molecules obey the octet rule, but there are a few that don't. That can have more than 8 electrons, or actually fewer than 8 electrons. The first exception, of course, is hydrogen. Hydrogen only needs 2 electrons to have a full outer shell, and so hydrogen will only make 1 bond. Boron is actually a weird element that is content to make only 3 bonds and have 6 total electrons. And then generally, if a nonmetal is in the 3rd period or below, so what am I talking about? Silicon, phosphorus, sulfur are in the 3rd period, chlorine, arsenic, selenium, bromine. So if they're in the 3rd period or lower, they can actually have as many as 12 electrons, as long as it's the center atom. Now, if it's an outer atom, they're not going to have more than 8, but if they're the center atom, they can actually hold more than 8, up to 12. The reason why these is because they have some unfilled D subshells that can be used for bonding, and so it's a bit beyond this class, but you can have up to 12 electrons. Okay, so here's some examples. Phosphorus shows that the 10 electrons are the phosphorus has 10 surrounding it. Each fluorine has 8. So xenon tetrafluoride, most noble gases don't make compounds, but xenon, being really big, actually can do that. And so because it's allowed to have more than 8 electrons, of course it only has 8 to start with, so it doesn't really need any more, but it's allowed to make up to 12 electrons. So this molecule can exist.